go to any workshops or conferences to explain to anybody, but it might be important. And all I did was put it into a book that was published last year. So some of you know that I've been working for 60 years now on a series of books called The Art of Computer Programming. And last year, I guess I got my first copy at the end of October, what was volume 4B, which includes, which is half about SAT solving. But the other half is what I want to talk about now, which was kind of a surprise as I was working on it. And that's exact covering. The exact covering problem, which then would generalize. So the exact covering problem is is old and well known, and we call this XC for short. And you can see it as a matrix, for example, of zeros and ones. And to get an exact cover, the idea is you just want to choose a subset of the rows so that the sum is 1, 1, 1, 1, 1, 1, 1. So I want to choose a row so that every column is covered exactly once. Now, for example, if every row has exactly 2 ones in it, this is the problem of perfect matching, because we have you have a graph and we put a 1 under U and under V if there's an edge between U and V, and so if we have a perfect matching, we have a set of the edges so that every vertex is matched, right? If every row has 3 ones in it, then we have the problem of 3 matching. I mean, actually, there are different versions. I mean, also in the perfect matching problem, you have bipartite matching and general graph matching, and similarly for 3 matching, you could say that you have a tripartite graph, and you have boys, girls, and or let's say, well, anyway, I don't know, boys, girls, and pets, or something like that, and there's triples that are allowed, and you perfectly, and you have a situation where every boy and girl have a pet. Okay, so now if there's 4 ones in every row, Sudoku is one example, because you can express the Sudoku problem in this way. You have to get one. You have to cover every cell of the board. You have to cover every row. You have to cover every column, and you have to cover every box. And of course, there's many other exact cover problems where you don't have the same number of ones in every row. But a huge number of combinatorial problems, I knew were related to exact cover. Then you can extend it slightly and say that some of the columns you only want at most 1 instead of exactly 1. So I call them primary if you've got to have exactly 1, and secondary if it's at most 1. And they behave like slack variables in linear programming, because if you say it's at most 1, then I can add a bunch more rows that are optional that just add in the ones one at a time. But it's better to just think right offhand that secondary are a special category. Okay, so I started with this, and a familiar example of the case with secondary variables would be the n queens problem. So we have like a chessboard. We have 64 rows, and in each row, and the columns. I have a column for each row, and I have a column for each diagonal going each way. And so every queen, in this case, again, there'll be it's in a certain row, it's in a certain column, and then it's in two diagonals. And the rule is that we can't have two queens in the same diagonal, but we don't have to cover every diagonal. So that's an example of this case where we have secondary variables. Okay, now the big surprise I got when okay, let's go back. I guess I started playing around with data structures for this about 1990, and I wrote and I designed a kind of a fun thing I called dancing links, which was a nice data structure for doing exact cover problem. And I'm not going to talk about the data structure, but basically it was designed to be very easy to do backtracking and undo what you were doing. So every time I made a change to the data structure, it was really easy to unchange it later on when I back it up. And so I had this algorithm, and I solved a lot of problems for fun, including the n queens problem, which was a little bit interesting because most people who had studied n queens problem, they would only cover the rows. But I mean, at every choice, they would say, well, where should I put the queen in this row? But my method was symmetrical between rows and columns. So I might decide where should I place the queen in this column instead of always going by rows. Okay, so anyway, you can set up all kind of pentagonal problems and things like this. They're all special cases of exact covering. But the surprise was that I started to see lots of other problems that used a generalization which we call XCC, which is exact covering with colors. An optional U here for colors, depending on. Okay, now what does that mean? So we have our matrix, and we have the primary, and we have secondary. And in the secondary, if I have a one, that just means okay, you can have at most one of these. But in the secondary, I can also put things like A and B in different different colors. And the rule is you're allowed to have you're allowed to have two of the same color, but you can't mix the color. So they have in secondary row, most one color allowed. And so you can think of the ones as that each one has some other unique color that doesn't appear anywhere else, and that would be another way of saying it. So that's the problem of exact covering with color. And well, the nice thing about it was that I only had to add a few dozen lines of code to my original program for the ordinary exact coloring problem, and I had a solver for exact covering with colors. It just turned out, you know, I had to purify the colors, but I didn't remove rows quite as often. All right, so that was amusing. But then, as I started working with it, I started to realize this was a really powerful model, and it was really good at stating more and more problems. And so as years went on, I thought of more and more cases where I could where this thing XCC problems were applicable. And also when I was looking at more and more examples, I changed the name. So instead of rows and columns, I think of it. I now say options and items. And so the options. The problem is to choose options, and each primary item has to be covered. And that change in terminology is actually usually when you think of a problem that somebody gives you to solve, we say what are the options that I have to choose between, and it turned out to be that those words sort of automatically suggest a model. So to make a long story short, I found many hundred models that are in volume 4B for people to look at, that covering all kinds of combinatorial problems, and pretty soon I came to the conclusion to realize that every CSP is also a special case of this model. So for example, you know, in a CSP you have variables and domains and so on. So the idea is well, let's say that one of the items is the name of a relation, and so then you list all the options for the relation, and the values of the variables could be the color of that item. So the variables could be secondary items, and their colors are the values of those variables, and then the primary items to cover are the relations, and says, yeah, you have to choose which option, which tuple of the relation is the thing, but you cover every relation once. And so it turns out you can also model instead of giving all the tuples, you can also say the non-tuples of a binary relation and use secondary items to block those out. So here I have, so now in a situation where if I have a problem to solve, I've got three choices. I can use a SAT solver, I can use a CSP solver, I can use an XCC solver, or I can use my favorite programming language and write my own custom backtrack program, of course. But they all three of them are actually viable. And after 20 years, I've got a lot of very mature XCC solvers there, and who knows? This might turn. I think that the model for actually express from a user's point of view of setting up a new problem it is often easiest in the XCC sense, easier than making up a SAT model or another. So I work on problems. I translate from one model. I try the SAT solver, which comes better. And last year I wrote a new XCC solver, which is one of the most subtle programs I ever wrote, and I still haven't found any bugs in it. But I keep trying, and so I thought I'd like to advertise it today so that more people could experiment and see if there is really something here. It's conceivable that 50 years from now, people will have these three models and they won't remember which came first. Historically, when you have three things, one of them has to come be first in 1 second. And so I stumbled on this, not realizing how versatile it was going to be. There's also a further model, which is MCC, which is multiple with multiplicities, covering with multiplicities and colors. And this means that instead of, for the primary items, you don't say it has to be exactly one, but you give a range. You can say the range, it can be between 3 and 5 or 0 and 6 or whatever. So you give an interval for every primary item as to how many options it should have in the final solution. Now, I think Charan has worked it out so that if you want to get some examples, he's going to have a slideshow running every 5 seconds to change to another page of this book. And if you want to, so you have two options. You can either buy volume 4B, or you can try to use the version that was online a year ago, which I don't maintain, but it's available. It's available online, and the URL is get to my home page, and then say FASC 5c.ps.gz for PostScript gzip file. And so that's what he did a few minutes ago, and got this file that you're looking at that here. And if you change if you change 5C to 7A, you get the current draft of what I'm working on now for volume 4C, which is about constraint satisfaction. And last thing I wanted to say is that working with the CSP, I learned new data structures for representing domains, and Christine Somo showed me how to use so-called sparse set data structures to do the same kind of things I was doing with dancing links. And so I now, with Christine's help, we have this new XCC solver and several others with different heuristics that use the sparse set data structure instead of dancing links, and she gave a beautiful name to this, dancing cells. So we call it the dancing cells data structure, and with some friends, we've been running hundreds of examples of all kinds, and we're finding that dancing cells is winning about 2/3 of the time, sometimes by a factor of 2 or 3, but it's consistently good. But sometimes the old dancing links is a winner, and I haven't yet figured out how to get my MCC solver onto sparse sets, but should be possible. Okay, question?
Does the solver do backtracking or look ahead? Does your solver do local look aheads?
The solver, yeah, so it uses forward checking essentially. The main one. So in other words, after I choose which primary item I should try to cover next, and maybe there's only one option left, so that's forced. But nice cases, there's only 2 options. So I try the first one, and branch on it now, and once I choose an option, then I throw out all the other options that clash with it. That means they've already been covered in the primary column, or it means that they have the wrong color in the secondary column. And so then it's time to cover something else. I keep going this way and then back up. And the beautiful thing about the sparse set data structure is that it's very fast to back up. The nicest thing is actually it can stop in the middle. As soon as I find that something's been wiped out, it's easier for the sparse set data structure to recognize this than for the doubly linked data structure to do that. And my new version that I did last year does more than forward checking. It actually does full domain consistency. And it was so what that means is that I can remove any option that no longer has support. For every option and every primary item, there has to be a way to use that option. Every option, every primary item not covered by that option. I want to make sure that applying this option isn't going to wipe out that other primary item. So I have to record a support for that, and that's a really tough problem, but I found a cute way to do it fast.
So this covering problem, we solved it in logic minimization. You've generalized that. So there's a covering matrix for figuring out the prime implicants of a function,
Yes.
and choosing the minimum prime set of prime implicants that covers all of the minterms.
Yeah.
And here the rows have a cost. I'm sorry, the columns have a cost in your case.
Yeah.
I think you tended 90 degrees, so I'm kind of a little confused.
Yeah. Okay.
And one of the problems with it is sometimes one of the dimensions of this matrix is exponential. The
Yes.
number of rows or number of columns is exponential.
Yeah.
Or maybe both can be exponential. And we've tried to encode this with set to do implicit covering instead of enumerating them explicitly.
Yeah. So every CSP can be translated into XCC in several ways, into SAT in several ways, and every SAT problem can be translated into CSP in several ways and XCC in several ways. The prime implicant type of thing introduced two issues that first of all, it's not exact covering. You have the OR of prime implicants, but they don't have to be destroyed prime implicants, but still you want to cover each one. So that would be an MCC problem where the number is 1 to 10 instead of exactly 1. But also you mentioned having a cost function associated. So in volume C, I show how to add extra extension so that you get the min cost exact cover with colors.
One more question.
Also, there's an extension that finds a ZDD for all the solutions. It doesn't work for the arbitrary XCC problem, but it works for lots of them. And that means you got a fast way to count solutions instead of enumerating them one by one.
Okay, well, thank you
Okay,
very much.
Let's try to get a slideshow going for anybody who wants to.
Yes, we're also going to attempt to do a group photograph. Do we know where?
No. Well, I think we're exiting through the main entrance, and hopefully Drew will be there and tell us where to go.
Okay, then we'll thank Don again and let's have some photos.
Now? Yep.